Okay, so at the end of the last video, I demonstrated how to calculate the population and the sample standard deviation using the definitional formula. And I guess just one of the things that I kind of wanted to end on was sort of what the definitional formula is actually telling us. So as I mentioned here, the top part of this equation, the sum of, in parentheses, x minus the mean, and parentheses squared, is called the sum of squares, right? So it's the sum of the squared deviations around the mean. When we divide that by n, that gives us the average sum of the squared deviations around the mean, which is our variance. And then when we take the square root, it is the average distance of the scores from the mean, and that's our standard deviation. So if we were to treat this set of scores, this set of 6 scores, as a population, we would divide by n, or the total number of cases, and that would give us a standard deviation of 1.34. Population standard deviation of 1.34. We know it's population because we're using Greek letters. We also know it's population because we're dividing by n, not n minus 1. Now, I've also mentioned with the definitional formula that the sample needed to be adjusted by the degrees of freedom, which is n minus 1. We know this is sample because instead of having a mu, we have x bar, and we have an s instead of a sigma, and we also have n minus 1 in the denominator. Again, this top half represents the sum of the squared deviations around the mean. N minus 1 is the degrees of freedom. This total formula within the square root is our variance, and then once we take the square root, that's our standard deviation. And as we said, the sample standard deviation is routinely underestimates the population standard deviation because the fact that samples tend to be drawn more from the center part of a distribution as opposed to the whole distribution, and so the range of scores is going to be restricted, producing a smaller standard deviation than one would otherwise get if you got the full range of scores. So when we treated this as if this were a sample instead of a population, we then divided our sum of squares by 5, our degrees of freedom. That gave us a variance of 2.17 and a standard deviation, sample standard deviation of 1.47. Recognizing that, of course, the goal here is to have this accurately as possible represent the population standard deviation, which is why we're making that adjustment. All right, so what I wanted to do now, the definitional formula is useful because it allows us to understand and define what each part of the standard deviation formula is actually telling us. However, it takes a lot of extra steps, and there's a much easier way to calculate the standard deviation. And so what I want to do now is actually show you the computational formula. So we're going to move to a whiteboard here. Okay, so first thing I'm going to do is write out the computational formula for the population standard deviation. So population, so we're going to use the Greek letter sigma to specify that, and that's going to be equal the square root of the sum of x squared minus, the sum of x squared divided by n, and once that whole thing divided by n. So in order for us, so the reason that this is an easier formula is because there's really only 2 values that we now have to calculate. We need to calculate the sum of x squared, and we need to calculate the sum of x so we can square it. So if we start with our x values, which I'm going to use the same values that I used with the definitional formula so you can see that we're getting the same results. So we had a 1, we had 2, 2, 3, 4, and 5. So first thing we can do, oops, sorry, did not mean to do that. Okay, well, that was interesting. First thing we can do is get the sum of x, which is 1 plus 2 is 3, plus 2 is 5, plus 3 is 8, plus 4 is 12, plus 5 is 17. So sum of x is equal to 17. The next thing that we need to do is get our x squared values so that we can add those up. So we have 1, 4, 4, 9, 16, and 25. 1 and 4 is 5, and 4 is 9, 18, 24, 29. We're going to carry that 2, and 1 is 3, and 2 is 5. So our sum of x squared is 59. So we now have the two values that we need to plug into our formula. So we're going to say, okay, so this is equal to the square root of. So sum of x squared is the sum of the squared x values. So that's going to be 59 minus 17 squared divided by 6, because that's our sample size, and the whole thing divided by 6. So we're going to do this again now, and now we've got 59 minus. Now, one of the quick checks that I had mentioned to you guys earlier is that the sum of x in parentheses squared is always going to be a larger value than the sum of the squared x values. So this is going to be 289 divided by 6, once again divided by 6. And now that's going to give us 59 minus 48.17 divided by 6. Sorry, that should be a square root there. And then that's going to give us 10.83. Now that value should look familiar to you because that was the sum of the squared deviations that we got when we used the computational formula. So I'll just pop right back there for a second to show that to you. So you'll see we got 10.84. So a little bit of rounding difference, but we're getting roughly the same number. Okay, and so 10.83 divided by 6 is going to be equal to the square root of 1.805. And again, if I were to quickly pop back to our slides, and we need to go back to our population, we see we have 1.81. All right, and that's going to give us a standard deviation of 1.35. And essentially what we got when we did it with the definitional formula was 1.34. Again, issues of rounding errors. Okay, so the advantage of this, as I said, is it's a simpler formula to use. It's a lot quicker, and you have fewer steps in order to get there. Now, if I wanted to do this with the sample standard deviation, let me erase all of this. If you'll bear with me. Wait. Oh, sorry. So we need to erase all those parts here. I'm going to keep my x and x squared because all that information is going to stay the same. Apologies for how long that's going to take. Okay. All right. Now, so if we recall, our sample computational formula is going to be, sample standard deviation is going to be specified by the small letter s. And we're going to have, again, in this case, the sum of x squared minus the sum of x squared divided by n minus 1. So what you're going to notice is that top value is going to be the same for both the population and the sample standard deviation. So if I pop back here real quick, what we're going to see here is that we had 10.84 for the population standard deviation, and we had 10.84 again because the sum of the squared deviations does not change. What changes is the variance and the standard deviation when we are looking at the sample. Okay, so the sum of the squared deviations is the same. We adjust at the point of the calculating the variance and the standard deviation. Because of that, that actually saves us some steps, right? So instead of having to go through this whole process again, I know that in my previous example, I knew that the sum of the square deviations, the top part of the formula was 10.83. So I'm not going to repeat that. This is going to be 6 minus 1, which is going to get me 10.83 divided by 5. And that's going to give me square root of 2.17. And ultimately, that's going to give me a standard deviation of 1.47. So if I were to flip back just to show you that this formula produced exactly the same values, right? So we got 2.17 for our variance and 1.47 for our standard deviation, both here using our computational formula and here using our definitional formula. So important to know how to do the definitional formula so that you understand what each part of that equation is actually telling us about the variability in the scores. But once we move forward, you'll have the option to use either the definitional or the computational formula. And for ease of work, I would say that the computational formula is probably the way to go. All right, so that's it. We'll do some of these examples in class.